brominations. So continuing on to the reactions of enolates, let's talk about how we get halogens inserted into that alpha position. Much like previous reactions, you can do this under acidic and basic conditions, but you'll see that there's a difference depending how exactly you end up doing this. So under acidic conditions, the first thing that you do is technically protonate a carbonyl. Now here I'm showing you the entire reaction setup. You use a catalyst, an acid catalyst for the reaction. You have your elemental bromine or elemental chlorine already present in solution, and this reaction relatively goes smoothly. You can have all three of these components at once combined together to yield the desired product. The way that this then happens is that you first protonate your carbonyl, the way that I talked about before, as far as forming the enol. And that's technically what's happening right here. You protonate the carbonyl oxygen, which then activates the alpha hydrogen for abstraction. So the water molecule that was formed in the first step attacks that proton. The electrons of that CH bond are reallocated towards the carbonyl carbon, and then the electrons of that carbon-oxygen double bond get kicked back over to the oxygen, which forms the enol. And this sequence, right, which I told you happens under acidic catalyzed conditions, which is absolutely what we're dealing with in this example, is the entry point for the actual substitution reaction that's about to happen. Because once this ketone has been tautomerized into its enol form, well, now the oxygen with its two lone pairs can have one of the lone pairs come back down to reform the double bond. But in doing so, what will happen right here is that the carbon-carbon double bond will become a nucleophilic attack set of electrons towards the electrophile. So you'll have that one of those two electrons out of the 4 pi system that we have here. Well, technically it's a 2 pi system, but 4 electrons in total, right? 2 electrons will go and attack the bromine, and you'll break up that bromine-bromine bond. In the process, you now have a brominated product. Mind you, you still have your oxygen protonated. So in the last step, you basically have that bromide that has been formed. Remove the proton, yielding back your now brominated ketone. So as you can see, the procedure is relatively simple, but it does go via the enol intermediate. That's really going to be the theme of this lecture as we go through the rest of the videos. Now, under basic conditions, there's a couple things that we need to consider. Now, the first thing is that if you want to end up with the same product that we got under acidic conditions, then you have to ensure that your enolate is produced to completion. And the way you do that is by ensuring that you mix your ketone or your aldehyde with a very strong base, absolutely stronger enough that it can completely remove all the alpha protons. So in this case, I'm depicting right here the protonated amine base, a bulky one. This is called hexamethyl disalicide, lithium hexamethyl disalicide to be exact, which is a very strong base. It's pretty bulky as well. It deprotonates the alpha hydrogen. And in this particular reaction, the way you have to do it is in 2 steps. So this is not a one-pot reaction like we did for the acid catalyst, where you mix all 3 of these things in one round bottom flask and you let it go. Here, absolutely, that would be very ill-advised and rather wasteful to do. Instead, what you have to do is first produce the enolate, the lithium enolate, by reacting ketone with your lithium deprotonated amine. And this enolate is then introduced to Br2. But you first have to form the enolate to completion. Like all of the ketone must be turned into enolate. Until that happens, bromine is not added. But once you have reached completion for this deprotonation, then bromine is introduced into the system and you get your direct substitution to happen. And as far as the mechanism goes, right, you have your deprotonated amine, which has the conjugate acid has a really strong, really high pK, much higher than that of ketones. So this reaction is guaranteed to go to completion. and you end up attacking the proton. Now, another reason to also use rather big bases, although you'll see a little bit down in the lecture that there are options to how big the base can be or how small. But one thing that you could also make use of is that by making this bigger, you make it a little bit harder for it to try to attack the carbonyl carbon, which you might have been wondering, like do those nucleophilic additions just like disappear? And the reality is that no, they don't. They all happen, and all these things are equilibriums. So the, it really depends on how you set up your conditions to kind of have the reaction manifest itself in one way versus the other. So you're really manipulating the conditions and the outcome of the reactions. So here, the deprotonation takes place. The electrons move over from that CH bond over to the carbon-carbon double bond, and then you break apart that carbon-oxygen double bond, creating your lithium enolate. In the process, you have also formed now the conjugate acid of the deprotonated amine, so just regular amine. And now that you have the enolate, well, the enolate can then be introduced to Br2 or vice versa. Br2 can be introduced to the lithium enolate solution. The electrons will come back down to reform the oxygen carbon double bond, and then the electrons of that alkene will attack Br2, breaking up that Br-Br single bond and yielding the monobrominated ketone. So that's the way you will have to go about it if you just want to end up with one bromine. Now, an interesting addendum to that last reaction that we talked about is that you can still perform it using a weaker base than necessary for the process. Now, here you have no choice. The reaction will never go to completion to the enolate state. If you use a weaker base necessary, you're going to get a tiny amount of the carbonyl to be turned into an enol, or enolate in this case. And so what's going to happen is that anytime during the course of the reaction, you're going to have significant amount of um, ketone, regular ketone, with a little bit of enolate. And as it turns out, and we will find out this in the next lecture, um, a ketone can react with its own enolate. So for that reason and that reason alone, you have to have the Br2 present from the very get-go. It has to be there. And if it isn't, then something else is going to happen, and these things are going to get pretty messy. But even then, having the Br2 around in the presence of the hydroxide, in the presence of the regular ketone, doesn't just give you monobromination. It actually continues forward to give you polybromination. And not only that, but after the alpha carbon gets fully brominated, assuming that it had 3 protons to begin with that could be substituted by bromine, the tribromomethyl group in here is actually completely removed and replaced by an oxo group. So I'm basically going to walk you through how that whole thing happens. And the tribromomethyl group ultimately becomes tribromomethane, also known as bromoform. So this is all done in one pot reaction. All right, so I already highlighted this, but just to make sure that we're on the same page, the pKa of water is less than 16, whereas the pKa of aldehydes and ketones is in the teens, right? Like 17 up to 20. So hydroxide is a much weaker base. So you're going to have an equilibrium that is less than 1. You're going to be favoring the reactants over the enolate product. So you just have an equilibrium at best, right? And this is how it goes. If you have the hydroxide, then some of it will actually react, and it will remove the alpha proton, having the electrons come here. And then for simplicity, I'm just going to keep the electrons on the carbon, just keep it at the carbon ion state. But just remember, this is an enolate, forming that oxygen lithium connection and your carbon-carbon double bond, more accurately. But, we're going to keep it like this. It's the resonance structure of it anyway. So you deprotonate that to some extent, and then the small amount of enolate that's formed attacks the Br2 that's present in that solution. It breaks apart that Br-Br single bond and forms the monobrominated product. And you would think, okay, well, that's literally what we saw in the previous mechanism, the previous reaction, where we did use a very strong base. The difference, however, is that this formation only represents at best 1% of all the ketone that was around. And so what that means is that if you're doing this under stoichiometric conditions, that means that 99% of sodium hydroxide is still haven't been used, 99% of Br2 still hasn't been used, and 99% of the original ketone still hasn't been reacted. So you have a lot of reactants that are still kind of like lingering around. And specifically, in the case of hydroxide being the best base available in this system, is looking constantly for the best acid present in solution. And the moment you monobrominate that alpha position of the carbonyl, guess what? You have just introduced a more electronegative atom. Therefore, you have rendered that residual alpha hydrogen more acidic than what you had before. So in other words, the ketone with which you started the process had less acidic protons, but now that it's brominated, those protons are more acidic. And so the moment this happens, now if it was reacting to some degree with the regular ketone, now this is going to react even more so with the monobrominated product. And so you'll have the actual deprotonation happening, right? Attack the proton, electrons come back here to reform the enolate. And then that enolate, because there's still quite a bit of Br2 present in the reaction flask, it will attack another molecule of Br2, breaking that Br-Br single bond and now giving you a dibrominated product. And you might already know where we're going with this, because if one bromine makes the residual proton more acidic, well, now two bromines are going to make the residual proton even more acidic than before. So this thing is reacting by default, right? If the other two did react, this one is reacting, like, absolutely. So you'll have that deprotonation happening again with the excess hydroxide that's still present in solution. The electrons will come back to the carbon to give you the enolate. And then that enolate will react with another equivalent of Br2 that hasn't yet been used up because of the small equilibrium. And that will break up that Br-Br single bond, right, and give you a tribrominated product. Now, technically speaking, this could continue with the opposite end of this ketone. So yes, that is a possibility, but I'm gonna, uh, you know, ignore that little fact for this discussion, because what needs to happen now is explain what happens with that tribromomethane group. All right, so the moment that you kind of have run out of alpha hydrogens, the next thing that happens is that because you still have a bunch of hydroxide, and although hydroxide is a strong base, it is also a fair nucleophile. The moment you have these three bromos here, no more acidic hydrogens, well, now you have basically render this carbonyl carbon even more attractive for nucleophilic attack, because all the bromines are withdrawing electron density away from that carbon the same way that the oxygen is withdrawing electron density away from the carbon. So this becomes really attractive towards hydroxide, so much so that it attacks that carbonyl carbon. It breaks that carbon oxygen double bond. It gives you the following intermediate. And you might think that this is ultimately is going to give us a gem diol like we saw in the aldehyde ketone chapter. But the thing is this: the three halogens bound to the same carbon, as a result of their electron withdrawing ability, make this carbon just decent enough of a leaving group under basic conditions that the carbonyl bond can actually be reestablished. And we have the, yes, we have the lone pair of that oxygen coming back down and forcing, if you will, that trihalomethane as a relatively okay leaving group, right? So in this case, the tribromomethane group leaves altogether. So we have tribromomethanide, and what you have left over is a carboxylic acid. Now, even though you do have the three bromines on carbon, you're still dealing with a carbon ion, so there's no way that this will be less basic than a carboxylate would be. So the last thing that happens is that this strong enough base is going to attack the carboxylic acid, remove that proton, turn it into a carboxylate, and in the process end up with a neutral tribromomethane molecule right here, bromoform in other words. Now this last step is irreversible because the pKs are such that, yeah, this will not go back. So this is in essence what kind of drives the reaction to completion. And then right here, just for reference, the pK of um, bromoform is about 14. And if you kind of think about it, right at the stage where the hydroxyl came in, right, and before we formed the double bond, we technically had two options. The tribromomethane could have been a leaving group, or the hydroxyl itself could have been a leaving group. But if you consider that the pKa of the conjugate acid of tribromomethane is 13.7, and the pKa of the conjugate acid of hydroxide, aka water, is 15.6, the fact that the pK of tribromomethane is lower means that it is a better leaving group. So that's another way to kind of look at it. Okay, and this is just for your information, but chloroform, which is the trichloro derivative, right, of this reaction, is basically a clear liquid for the most part. Bromoform has a little bit more of a yellow tint to it, and by the time you get to iodoform, where you use iodine, not only is the material highly colored, but it happens to be a solid because you have a lot of molecular weight at that point present in this molecule. So this is one of the ways in which chemists back in the days used to determine whether or not there was a ketone that happened to have a CH3 attached to the carbonyl carbon by seeing this iodoform crashing out from the solution. So it was a visual test. But that's kind of the ingenuity that all the chemists from the 1800s, 1700s would come up with to determine the structure of molecules. So yeah, I mean that's really amazing if you ask me. Okay, in the next video we're going to talk about other types of reactions that do involve halogens. In this case, the Helmholtz-Zelinsky reaction, and I'll tell you all about it in the next video. So I'll catch you then. Bye bye.